So I originally thought that the motion of our yo-yo could be explained the same way you would explain the motion of a spring.
But wait, Michael, that'd be incorrect. Now, by looking simply at the pictures, you could say that they are very similar, but a spring is a little bit different. We still have the force of gravity always acting on it, but then we also have to incorporate the force of the spring. So up here, the spring's compressed, it's pushing down. And then as it falls and it hits the equilibrium line, there's no force of the spring, only the force of gravity happening. Past this, the spring will be slowing down the block. Then once we get here, we still have force of gravity, but now the force of the spring is acting in the opposite direction, bringing it back up to slowly bring it back to equilibrium.
So in contrast, the yo-yo actually maintains the same angular momentum throughout. So you have gravity acting on it downwards, and the tension force in the string causing it to spin. And then once it reaches the bottom, the angular momentum is still going this way, using the right hand rule. It's rolling this way, and so this will roll upwards. But
Still staying in the same direction.
yeah. That's all.
Alright, hello. So in our yo-yo project, gravity and friction are two factors that play into this experiment. Gravity is obvious, we are on Earth, so when we let go it falls. And then friction is what allows us to harness the energy that is created. So as it's falling, it gains rotational momentum, and then when it reaches the end of the string, it's still spinning, so it goes back up. And the way we were able to harness that is with tape, which creates friction. We found that when we were building it, when we just had a loop of string and it hit the bottom, it would just spin at the very bottom and wouldn't roll back up. So we were able to use tape to be able to harness
momentum,
make it go up and down a lot more effectively.
What causes the rod to spin as it falls? If we just drop this without a string, it would fall straight down, maybe a little bit of spinning just due to like an offset release. However, when we drop it, it spins, giving it angular momentum. So why is this? We drew a free body diagram to figure this out. So gravity acts on about the center of this, the center of mass. And there's a force of tension from the string pulling up, us holding it, or the device we built holding it. And since these aren't equal, it's gonna have like a rotational point around that, because the forces aren't acting in the same point. So since they're acting offset of each other,
causing torque
in a twisting motion. So as the disc falls, it gains angular momentum, which means that the omega and inertia are increasing with time, so it basically is speeding up in rotation as it falls, as well as having more momentum in the circle that it is spinning. So when it reaches the bottom, the string grabs onto it once it's at its end, then starts winding back up, and it rotates in the same direction. However, since it's grabbed on the other side of the string, like this, it's grabbing onto the other side and it winds up on the opposite side, which means it's spinning in the same direction but traveling in the opposite direction.
In order to find the rotational inertia of the object, I broke it up into three separate objects, being the left side of the rod, the right side of the rod, and a disc in the middle. Which, if I add them up, I get the rotational inertia of the yo-yo. Which, since the left side of the rod has the same radius as the right side of the rod, they have equivalent rotational inertias, so I can just multiply it by 2, add the disc, and I'll get the rotational inertia of the yo-yo. Knowing the rotational inertia formula for a disc, I can just plug that in right there. And this disc here actually has a radius of this R1 plus this R2, which gives me the radius of the disc. And these twos cancel out. This plus this equals this.